question is, suppose the following disk request sequence, that is track numbers for a disk with 100 tracks is given, and the sequence is 45, 20, 90, 10, 50, 60, 80, 25 and 70. Assume that the initial position of the read-write head when starting is on track 50. The additional distance that will be traversed by the read-write head when scan or the elevator algorithm is used as compared to the shortest seek time first algorithm is dash number of tracks. So you have to assume that the scan algorithm moves towards 100 when it starts. Okay, so basically you are given a sequence of different track numbers that are requested, and you have to find a comparison between the scan algorithm or the elevator algorithm and the SSTF algorithm, which is shortest seek time first algorithm, and you have to tell the difference. Okay, so please read the question carefully. It is asking additional distance that will be traversed. All right, so starting with the SSTF algorithm first, in shortest seek time first, what do we actually do? We traverse or we move the head to the next request, that is the nearest one to the current head location, or the request to which the seek time of the head will be the least. So let us first place all the numbers or the disk requests that will be generated by the sequence or the system. So the disk requests can range from 0 to 100, and the increasing order in which the requests are made is 10, 20, then we have 25, then there is 45, then 50. 50 is the current position of the head. Then we have 60, 70, 80, 90. Alright, so 90, and please ignore this line, and this is 100, or you can write 100 here. Okay, so initially disk is at this position, and since 50 is a particular request, that means we have to serve a particular request at track 50, so we serve the first request here itself. Okay, then the shortest distance or the shortest seek time from 50 can be either to 45 or to 60, but 50 minus 45 is less than 60 minus 50. Therefore we move towards 45 and service 45 here. Alright, this requires a seek time of 5 units. Now from 45, the least request will be from 45 to 60, which requires a seek time of 15 units instead of from 45 to 25, which requires 20 units. So from 45 we move to 60 and service this request, which makes or which uses a 15 units of time. Then from 60, definitely the nearest one is 70, that makes use of 10 units. Then 80, again 10 units, then 90, and then we stop, because 100 is not a request. Okay, it is the end of the disk, and there we do not have to serve any request. The next nearest request will be at 25 at this position. All right, so from 90 we turn and go towards 25, and this requires 65 unit of time. Okay, 90 minus 25. From 25 we need to service 20, which is the nearest, that requires 5 units, and from 20 we come to 10, again requiring 10 units. Alright, so all these requests are serviced, and now let's sum up and find out how much actual time is taken. So for SSTF, the time that would be taken would be, initially at 50 we have serviced one request, so that is 0. Then 45, that requires 5 units. Then 60, which requires 15, and we sum up like this. Then 65 units, then 5 units and 10 units, and when you calculate and perform this addition, you will get a total of 130 here. Alright, so now let's start with the scan algorithm. Here, scan algorithm would generate a different amount of time, and we have to tell how much, what would be the difference here. So the scan algorithm, what does it do? It starts in one particular direction and it services all the requests that are made in that direction. Alright, and after servicing all the requests in that direction, it reverses the head and moves in the opposite direction, servicing all the requests when it moves to the other end. So if it starts, suppose, somewhere at 50, it will, since we are told that in the scan algorithm we have to move towards 100, so it will start from 50 because the current head is at 50, and it will service all the requests while going to one end of the disk, which is 100, and it will go to 100 also, to the extreme end of the disk, and then it will reverse its direction and come back till the first request. Okay, so now let's number the requests just like we did in the previous traversal. So 10, 20, 25. This is 45, then 50, where that is the location of the current head. 70, 80, 90 and 100. This is the end. Okay. So initially our disk head is at this position 50 and one request is serviced here. It is moving in 100, the direction towards 100, so we do not have to check or think of anything else. We have to move towards the right and service all the requests that come in our way. So first 60 is serviced, then 70, then 80, then 90, and it will go till the extreme end to 100, even if 100 is not a actual request. So how much distance or how much time is taken? 10 in each case. All right, now it reverses its direction and services in the opposite direction. So from 90 it will come to this point, which is 45. So it comes here and services this request. So 90 minus 45, sorry, 100 minus 45 is 55. From 45 it will go towards the left and service all the requests. So this is 20, then 25, and then towards 10, and it goes till 10, and it will stop here because there are no more requests. Here it reached the end because there were more requests to service. Here it will stop at the last request. All right, so we have to sum up all these values and find out how much time this scan algorithm is taking. Okay, so plus 55 plus 20 plus 5 and plus 10. So if you sum this up, this will come 50 plus 55, 105, 125, 130 and 140. So a total of 140, which is 10 more than 130. So the answer is 10, because I told you initially also that you have to tell the difference. So 140 minus 130 is 10 tracks. So that is question. The question says that consider the following two process synchronization solution. You are given two processes, process 0 and process 1. Process 0 is that at the entry point there is a loop while turn equal to 1. Then if this value becomes false, turn becomes 0, this loop will terminate because there is a semicolon here. Then the process will enter into its critical section and then it will exit after making the value of the variable turn equal to 1. And similarly we have process 1, which checks the value of variable turn in its entry condition, which is again a while loop which will continue to infinitely as long as the value of turn is 0, and as soon as the value of turn becomes 1, this process will come out of the while loop and enter its critical section. After completing the work of its critical section, it will come out and make the variable turn equal to 0 and exit. Okay, so the question is, the shared variable turn is initialized to 0. Which one of the following is true? This is a correct two-process synchronization solution. This solution violates mutual exclusion requirement. This solution violates progress requirement, or the last part is that this solution violates bounded weight requirement. Okay, now all the last three parts state different terms and we need to be very clear about each of them. So starting with mutual exclusion, what is actually mutual exclusion? Mutual exclusion means that at any particular time only one process can execute in its critical section, and at no time two processes would be simultaneously having access to their critical section. Okay, so I'm writing mutual exclusion. Sorry. Mutual exclusion, that means only one process at the max can execute in its critical section at any point of time. Okay, this is the condition of mutual exclusion. Now in this question, the decision of which process will enter in its critical section is taken by the while loop that is present at the entry point. Okay, so if any time both P0, that means process 0 and process 1, P0 and P1 try to enter their critical section, that means at the same time they test their while condition, turn equal to 1 and turn equal to 0. Now if this happens, then since the value of turn can either be 1 or it can be 0, it cannot be both. Therefore, depending on what is the value of turn, that process will be allowed entry into the critical section and the other process will not be allowed entry, and therefore the other process would have to wait. Okay, so if P0 and P1 are both trying to enter their critical section and the value of turn is suppose 1, so P0 will be stuck into its loop because it will keep on executing this loop as long as turn is equal to 1, and since process 1 finds that this condition is false, therefore it will enter its critical section. Okay, so one process executes and then it gives the control to other process to execute. So the principle of mutual exclusion is followed and it is not violated. So this option becomes false. Now coming to the next part, progress and bounded waiting. So let's understand bounded waiting before we understand progress. Now, what does bounded waiting means? Bounded waiting means that if a particular process has requested to enter its critical section, so I'll write it here. If a process has made a request to enter its critical section, then there is a limit on the number of times other processes are allowed to enter their critical section before this request made by this particular process is granted. Okay, so it basically means that a process who is requesting access to its critical section will not wait infinitely. It would wait and there would be a limit or a bound on its waiting. Okay, so if a process has made a request to enter its critical section, then there is a limit or a bound on the number of times other processes are allowed to enter their critical section before this request is granted. Allowed to enter their critical section before this particular request is granted. Okay, so now let's see if this concept of bounded waiting is fulfilled here or not. Now in this case, in our case, if P0 has requested to enter the critical section, therefore currently if P1 is executing in its critical section, so if P1 is executing, it means it had found the value of turn variable as 1. So initially or at a particular time, if turn is equal to 1 and P1 enters in its critical section, then after executing its critical section, it will come out and it will make the value of turn 0. Now since process 0 had requested to enter its critical section and it will now find turn equal to 0, therefore it will now get its chance to enter its critical section. So there is a limited amount of time that any process, either process 0 or process 1, will wait when it has requested to enter a particular critical section and some other process is executing in its critical section. Neither of the process will wait indefinitely. Okay, so this part is also incorrect because the condition of bounded waiting is also fulfilled here. Now when you carefully notice, when I stated here that when a particular process enters its critical section, it reverses the value of the variable turn after completing its work. So basically a process does its work in the critical section, reverses the value of turn, and if now this same process has to execute its critical section again, first the other process would have to reverse this value again, then only the process would get another chance of entering its critical section. So let's understand this, and this point would be helpful to you in understanding the C part, the progress requirement. So if initially turn is equal to 0 and process 0 enters its critical section, after completing its critical section, it sets the value of turn equal to 1. Now suppose at this moment process 0 again wants to enter its critical section and process 1 does not want to enter its critical section. But since the value of turn is equal to 1 and this value can be reversed to value 0 only by process 1, therefore it is required that to give another chance to process 0, or process 0 will get another chance into its critical section only when process 1 enters its critical section and reverses this value of 1 to 0. Alright, and this means that there is a strict alternation between these two processes. So strict alternation means that each process would enter one by one, and this has to be true even when a particular process requires more than one chances. Each process has to enter one by one to give the next access to another process. Okay, so strict alternation means that after completion of P0, if we are considering P0, if it wants to execute critical section again, it will have to wait until process 1 executes once and gives lock to P0 again. Okay, but this strict alternation violates the progress requirement. And what is the progress requirement? Progress requirement states that no process that is executing outside the critical section is allowed to make or enter into a decision of which process would enter in the critical section next. So what does it mean? That now P0 wants to enter into critical section again, but we are dependent on process 1 to allow this entry of process 0 into its critical section again. But process 1 is not entered or is not executing in its critical section, and still it is being a part, or it is playing some role in deciding whether process 0 will enter its critical section or not. Okay, so even when process 1 is not executing in its critical section, still it is a part of deciding whether process 0 will enter its critical section or not. Okay, and how is it a part? Because only when process 1 executes and reverses the value of variable turn, then process 0 would get a second chance. So no process executing outside its critical section is allowed to stop a process that is interested in entering its critical section. Okay, so progress requirement is violated here, so the correct answer is C. Alright, so in this question you need to understand what are the three terms. These are the basic three terms that are required in process synchronization problems. These three terms, when you understand them completely, you can easily solve all the questions based on this topic. So that's all for today's lecture. Thank you for watching our video. Stay tuned to Easy Engineering classes for more lectures on our preparation series of various computer science exams as well as other computer science related subjects. Thank you.